All right, today we're going to dive into this incredible, invisible world that honestly keeps our entire society running and our waters safe. We're talking about wastewater treatment, and more specifically, the microscopic workforce that does all the dirty work for us. Seriously, have you ever stopped to think about it? You flush the toilet, you wash your hands, and poof, the water's just gone. But where does it actually go? I mean, it has to go somewhere, right? Well, the answer is way more fascinating than you probably think. Yeah, it definitely doesn't just vanish. Instead, it flows into a massive, super sophisticated facility, kind of like this one. And you look at this, and you see all these pipes and tanks, and it looks like some kind of industrial factory, right? But the real magic, the secret sauce, isn't the concrete and steel. It's the trillions of living organisms inside. It's basically a microscopic workforce that we've put in charge of one of the most important jobs on the entire planet. Okay, so let's metaphorically step inside this factory and see how the whole thing works. We're going to follow the water on its journey from, well, dirty to clean, and we're going to meet the tiny workers responsible for making it happen. So after the water gets some initial screening, to get the big stuff out, it ends up right here. This is the heart of the whole operation, the biological treatment stage. And you can see it's got two main parts. There's the aeration basin, that's kind of like the factory floor where all the work gets done. And then there's the secondary clarifier, which is where the workers get separated from the finished product, the clean water. This whole setup is pretty much the office, the factory, and the cafeteria all rolled into one for our little microbial employees. So who exactly are these workers we keep talking about? Well, they're not little people in hard hats, that's for sure. We're talking about a super complex community of bacteria, protozoa, and all sorts of other microorganisms. Let's get properly introduced to the team. Okay, the official technical term for this workforce is activated sludge. And I know, sludge doesn't sound very glamorous, but it's not what you're picturing. This stuff is a living, thriving ecosystem that we've engineered. It's basically a super dense soup of life that we've put to work to literally eat pollution. Their job description, when you break it down, is pretty simple, but it is absolutely critical. First things first, they eat. Their food is all the organic gunk in the water. Second, as they eat, they grow, and they make more of themselves, which keeps the workforce copulation nice and stable. And third, and this is super important, they have to flocculate. That's just a fancy word for clumping together. They form these little groups that get heavy enough to sink, which is how we separate them from the clean water later on. Now, you can't just let your workforce grow forever, right? I mean, just like any factory manager, the plant operators have to control the population. And their number one tool for doing that is something called solids retention time. You'll hear it called SRT. Okay, I know what you're thinking. You see a formula like this and your eyes might start to glaze over. But hang on, because the idea here is incredibly simple. All it is the total amount of microbes you have in the system divided by the amount of microbes you're taking out each day. Seriously, that's it. So that calculation gives us the solids retention time, the SRT. And the best way to think about it is as the average career length for one of these microbes. How long does it work in the plant before it gets, well, retired? Is it 5 days? Is it 30 days? That one single number is one of the most powerful dials an operator can turn to control the entire system. And this brings us to a really, really critical point. There's a bare minimum for that career length. It's called SRT men. If you go below that, if you start removing your workers faster than they can reproduce, your entire workforce just collapses. The whole system fails. As you can see here, if that happens, the pollution just flows right through untreated. It's a biological crash, and it's not just some small operational problem. It's a potential public health emergency. Okay, so we've figured out how to manage the population size with SRT. The next big thing to control is their food. How much is each one of these little workers getting to eat every day? And that brings us to our second key concept, the F/M ratio. The food to microorganism ratio, it's actually exactly what it sounds like. It's just the amount of incoming food, which is the pollution, divided by the total mass of microorganisms you have. So in our factory analogy, it's the daily food ration for each employee. Are we giving them an all-you-can-eat buffet or just a small snack? And here's the cool part. These two ideas, SRT and F/M, they're totally connected. They're like two sides of the same coin. Just think it through with me. If you have a high SRT, that means you're keeping your microbes around for a long time, right? So you build up this big, dense population of workers.
Now, if the amount of food coming in stays the same, you have to split that food among way more workers. So each individual microbe gets a smaller share. See how that works? A high SRT automatically leads to a low F over M ratio. And this table here shows you exactly what that looks like with some real-world numbers. Look, if you run a short career length, say 5 to 7 days, you get a high food ratio for each microbe. But if you stretch that career out to 20 or 30 days, that food ratio plummets. It's this perfect inverse relationship. And operators use this fundamental principle every single day to keep the entire plant perfectly balanced. But what happens if you lose that balance? What if that F over M ratio gets way too high? What happens when you basically overfeed your entire workforce? Well, believe it or not, they get kind of fat and lazy, and they stop doing their jobs right. And this leads to a really serious problem called
Sledge bulking. Yeah. When the microbes get way too much food, some of them start growing in these long, stringy filaments. So instead of clumping together and sinking like they're supposed to, the whole mass of sludge becomes fluffy. It gets buoyant and just floats. And if your workers won't sink, you can't separate them from the clean water. It's a total disaster for the whole process. And look, these ideas, SRT and F over M, they aren't just abstract concepts for the operators running the plant day to day. They are literally the fundamental building blocks for the engineers who design and build these massive, multi-million-dollar facilities from scratch. I mean, check out this quote from our source material. It says that the SRT is a critical design parameter. Engineers take that number, the career length they want for the microbes, and they use it to calculate exactly how big that aeration basin needs to be. Think about that for a second. The biology is literally dictating the concrete and steel architecture. And understanding these core principles, how to manage this microbial workforce, it's not just about keeping today's plants running. It's the key that unlocks the next generation of water technology. It's how we push the boundaries of what's possible. Take, for example, something called a membrane bioreactor, or MBR. You can see the difference here. On the left, you've got your traditional plant with those giant settling tanks. An MBR, on the right, basically takes that same activated sludge process, but combines it with super advanced filters. This lets them pack in a much, much higher concentration of microbes, which means they don't need those huge settling tanks anymore. The result? A way smaller plant, which is a total game changer for cities where space is at a premium. And all of this is leading to this really revolutionary idea. Once we truly master these biological systems, we can stop thinking about wastewater as, waste. What if we didn't just treat it at the end of the pipe? What if new tech allowed us to do what some people are calling sewer mining? I mean, what if our sewers weren't just for disposal, but for actually mining clean water and valuable nutrients right where we need them most? It just completely flips the script, It turns a massive problem into an incredible resource. That hidden world of microbes, it isn't just cleaning our water today, it's literally shaping the future of how we'll use it tomorrow.